All right, welcome. Today we're going to talk about calculus and particle motion. We'll be discussing S of t, v of t, and a of t, the position function, the velocity function, and the acceleration function, how they are related to each other, and we'll answer a few questions based off each. So let's get it. Oh, wrong voice. Let's get it. All right, so the question reads, we have the equation of motion of some particle is S of t is equal to t to the third minus 3t. And it tells us that S of t, which is the position, is in meters, and t is in seconds. So let's just talk about this function and what it represents, right? Whenever t, if you're given any t value, t is 1, t is 2, t is 3, those represent seconds, right? T is 0 would be the initial position. So think about if I plug in 0 for t, that would represent before time has even started. So the initial position of this particle would be at 0, right? If I plug 0 in for t, I'd have 0 to the third minus 3 times 0, which will give you 0. So at 0 seconds, the position is 0. Okay. At 1 second, we can say the position is 1 to the third minus 3 times 1. So 1 minus 3 is negative 2. So the position would be negative 2. Think about what that would mean. That would mean if I'm standing and I'm looking at my position, right? Before time begins, my position is 0. I haven't moved. At 1 second, my position's negative 2. So that would mean possibly I would move back to, in this case, meters, right? As time increases, position will change. So if I plug in 2 for t, I would have 2 to the third, which is 8, minus 3 times 2, which is 6. So 8 minus 6 is 2. Now my position is positive 2. So that means after 1 second, I've moved back to a negative 2 position. Then after the second, sounds weird, the next second, so when t is 2, I'm now at a position of positive 2. So I've moved between 1 second and 2 seconds, I've moved up 4 units, right? At 1 second, I was at the position negative 2. At 2 seconds, I was at the position positive 2. Now, one thing you do need to think about is time, in this case, is not negative, right? We cannot go into past. So the domain here, or this position function, is not defined when t is negative. It can't be defined when t is negative. All right, so the smallest t value is 0, which is the initial position, and then t can increase, and then depending on what this is modeling, t may be restricted again. It may not be able to, there may be a maximum value of t, but it all depends on what the position function is and what it is modeling. Okay, so if you type this into your calculator, you will type it in as x to the third minus 3x. You would hit the graph button, and you can get a general idea of what it looks like, the particle motion. Now we should see the particle go through 0, 0, because as we said, the initial position would be at the origin, 0, 0. When time is 0, the position is 0. And then as you can see, when time is 1 second, the position is at negative 2. When time is 2 seconds, the position would be positive 2. And as you can see, when t continuously increases to infinity, this function increases to the function values, the position values of positive infinity very rapidly. So that's what I was referring to earlier when I said sometimes the position function may also be restricted on the right side. Let me show you how to do this real quick. We know this position function only works, well, let me word it this way. This position function doesn't work from when time is negative, so we could actually let our graph reflect that. If you hit divided by and then open up some parentheses, type in x, and then hit second math, which is the test option, you get these inequality symbols. We want x to be greater than or equal to 0, so we'll go down to the greater than or equal to symbol. We hit enter, and then we want it to be 0. Close our parentheses. Now check out the graph. It starts at 0, 0, so it shaves off the negative x values, or in the case of our problem, the negative t values for the graph. So now we have a good understanding that this starts at 0, 0, and as the independent t values increase, then the position changes. Okay, so part A of our problem is asking us to find the velocity and the acceleration functions. Okay, so at this point, if you're watching this video, you should have a pretty good understanding of a derivative and what it is used to find. If I'm driving in a car, right, my speed is constantly changing unless you have cruise control on. But in general, your speed fluctuates. You know, if the speed limit's 55, you may go from 52 to 57, continuously changing between those speeds, right? But at a very specific moment in time, your speed is exactly 55 miles per hour or whatever, 57 miles per hour at an exact moment of time, right? The speed is the absolute value of the velocity. Velocity is either positive or negative, and the sign of the velocity actually tells us quite a bit. So if we look at this function and we are asked to find the velocity and the acceleration functions, s of t is the position function. The v of t is, of course, the velocity function. And then the acceleration is the a of t. You can find the position of this particle at any moment in time greater than 0, when t is greater than 0. But what if you're asked what's the velocity of this particle that's modeled with this position function? So that's asking you what is the rate of change at that particular moment. The velocity, being that it's a rate of change, is the first derivative of the position. So let's jot that down before we actually find the velocity function. Let's jot down some notes. I'm going to scroll down on the screen. I want the position function to stay on the screen. So we have the position function. Okay. The first derivative of the position function is the velocity function. Get that stray mark out of my screen. And then the acceleration function is the rate of change at which the rate of change is changing. Kind of confusing, right? Think about in a car, right? You have a position, you have a velocity, which would be similar to the speed at which you're traveling. But then you have the acceleration, which is how fast are you accelerating? Are you decelerating? Things like that. So the acceleration function is the derivative of the velocity function. But the velocity function is the derivative of the position function. So that means the acceleration is the second derivative of the position function. So let's jot that down. So s double prime of t is equal to v prime of t, which is the first derivative of the velocity, and that is the acceleration. Position function is a polynomial, so we would use the power rule to find the derivative. So in blue, we'll say if s of t is t to the third minus 3t, then the velocity function is the first derivative, which is, using the power rule, we would say the derivative of t to the third is 3t squared. And then the derivative of the negative 3t would be minus 3. So there is the velocity function. The acceleration function is the derivative of that. So if I take the derivative of the velocity function, then I have the acceleration function, which would be, what's the derivative of 3t squared? 6t. What's the derivative of -3? Well, -3 is a constant. The derivative of a constant is 0. So there are your 3 particle motion formulas. Now there is a fourth, it's called the jerk function, and you can simply take the derivative again to find the jerk function. But typically we use these 3, the position, the velocity, and the acceleration. So now let's answer some questions based off these 3 functions. All right, let's say we're presented with a problem to find the acceleration after 2 seconds. Well, now we have the function that models our acceleration. And so if I'm asked to find the acceleration after 2 seconds, I would say, well, that's a of 2. So acceleration at 2 seconds, which is 6 times 2, which is 12 meters per second squared. So make sure your units are correct. So let's go back and interpret the acceleration. The acceleration is the rate at which the speed is changing. So it's speed over time. So if the speed is, say, in this case, meters per second over time, which is over seconds, then that's going to be meters per second squared. All right. So in other words, meters per second, well, if you multiply by the reciprocal, you'll have meters per second times 1 over s, which is meters per second squared. All right, let's look at another one. All right, so the third question is going to say find the acceleration when the velocity is 0. So if we interpret that, the distance over the time is 0, right? So think about what that means. Your speed would be 0 at that particular moment. When the velocity equals 0, that's representative of where a horizontal tangent line lies. Okay, so in this case, we have a change in direction here, which it looks as though it's going to be when t equals 1. We have a change in direction, right? We begin at 0, 0, we go down to -2, and then we begin to move forward. Okay, so the change in direction would be where your velocity is equal to 0, where there's no speed. So think about, again, in a car. Let's say you're first backing up. Let's say you're getting out of a parking space, right? Your position 0 when you begin. You put it in reverse, you back up, and then you shift to drive, and then you go forward. So your speed at which, at the time that you switch from reverse to forward, your speed there is 0. All right. This question is asking, what is the acceleration when your velocity or your speed is 0? So let's pull the question back up. So the first thing we need to do is find when the velocity is equal to 0. So just like we just said, when is the velocity equal to 0? Well, here is the velocity function. If it lets me circle it, set that equal to 0. So I have 3t squared minus 3 equals 0. T is equal to plus and minus 1. However, in the context of this problem, the -1 doesn't make any sense. So we'll just say this is simply 1 second. So now it's asking what's the acceleration at that point. So then we will take the acceleration function, we would plug in 1, and we'd see that the acceleration is 6 meters per second squared. And there we go. I will hopefully create another video going a little further in depth, but I hope this helped. Look out for new videos. If you have requests of videos or something that you need help with, please let me know.